signal and the radical change in the data. The spectral data has a high peak, nearly 7 inches per second at a frequency of 5 Hertz. The rest of the spectrum appears as a raised floor, much like random impacting. Although the spectral data does not appear normal, it could be overlooked. But the waveform data immediately tells the story of an intermittent signal. This data was acquired during a routine monthly survey. If the program had been defined to keep only spectral data, this waveform, which provided the key to the diagnosis, would have been discarded. It is important to store the time waveforms during routine surveys. This waveform is from a slow-turning chain-driven roll. Notice how it is very asymmetrical. That is, there is much more energy on one side of zero than the other. In this case, the predominant energy is on the positive side. The asymmetry indicates that motion in one direction is limited, and there could be an obstruction. Or by design, the system may allow more freedom of movement in one direction. There appears to be some random impacting in the waveform. From the previous section on spikes and impacts, we know to expect to see a raised floor of the spectrum. But the asymmetry, due to a restriction of motion, clips or truncates the waveform in one direction so that it no longer is a pure sine wave at a single frequency. Remember Fourier's basic premise for a complex waveform. It is the sum of the harmonics of the repetition rate of sine and cosine waves. This is transformed to the spectral data as harmonics of shaft turning speed. The cursors mark the shaft turning speed harmonics. The other peaks are 1/3 and 2/3 harmonics. Another example of asymmetry involves a severe truncation due to a restriction of motion. This waveform data is from an unbalanced condition of a spindle that is mounted so that it moves easier in one direction than the other. Again, the restriction causes a clipped waveform that is no longer a pure sine wave at a discrete frequency. The FFT process adds the series of sine waves, which are the exact multiples of the signal generated from the turning speed. The resulting spectrum has turning speed harmonics. If we were to view this spectrum to determine the cause of the problems, it would be unclear. However, one glance at the waveform tells the story. This is another example of the value of using the waveform to aid in diagnosis. The source of problems can sometimes be difficult to detect. In motors, for instance, vibration can be caused by mechanical events such as imbalance, misalignment, mechanical looseness, or the vibration can be caused by electrical problems such as an uneven air gap, rotor bar problems, shorts in the windings, and others. Oftentimes, there is more than one forcing function in a machine, and two of the forcing functions may be so close together they appear as one frequency when the resolution is not adequate to separate them. A technique often used to determine the amount of energy attributed to electrical phenomena is to shut off the power while monitoring the data. Electrical energy will immediately drop out, while mechanical energy will remain through the coast down. The coast down can be monitored in the spectral or waveform data. Here we are using a single channel analyzer to monitor the waveform. Set the maximum frequency and sample size to capture the data, being sure that the sample time will not cause the shutoff to be missed. The fast update rate of the waveform helps ensure capturing the change as the machine is shut off. Notice the drop in amplitude as the electrical energy is removed from the waveform. This indicates that nearly half the energy is attributed to electrical events. When the coast down is monitored in the spectrum, the data is only as good as the update rate of the analyzer. In other words, as the waveform is sampled, the process time to perform the FFT and display the spectrum may cause the actual shutoff event to be missed. While the machine is running with a load, there is some fluctuation in the signal. Without adequate resolution, the multiple frequencies may appear as one, and the drop-off due to electrical energy may not be as noticeable. In this case, we see that there is substantial change in the spectral data as the machine is shut off. But to be certain to capture the event, the waveform will typically show the most information. Events that occur a few seconds apart are missed by many analysts, and problems that stem from these events can take an analyst by surprise. These events can occur in speed reduction gearboxes or may occur in typical pumps, fans and motors due to process variables or transient events. Normal routine data collection on typical equipment may not capture low-frequency or transient events. Equipment that has turning speeds of 30 to 60 Hertz may have only an eighth to a half second of time in the waveform. The length of time in the waveform is defined as the sample size divided by the maximum frequency times 2.56. The sample size is the number of data points in the waveform. In some analyzers, the maximum number of points is 1024. Other analyzers may be able to store more than 16,000 data points for the waveform. The maximum frequency is the highest frequency to be included in the waveform or spectral data. Routine data collection may include frequencies to 50 times shaft turning speed. If the shaft speed is 60 Hertz or 3600 RPM, the maximum frequency will be 3000 Hertz or 180,000 cycles per minute. 2.56 is a constant. This is how much faster the data must actually be sampled to achieve anti-aliasing of the signal. With 3000 Hertz as the maximum frequency, the time window in the waveform is only 133 milliseconds or 0.13 seconds. Remember that there are 1024 data points in this waveform. This means there is extreme detail for the 0.13 seconds. However, a short time waveform cannot capture multiple occurrences of low-frequency events spaced even a half second apart. If the maximum frequency is set to 200 Hertz and the sample size remains at 1024 points, then the time in the waveform is a full 2 seconds. This new waveform data from the same machine running in the same condition shows much more information. There is a repetitive cycle occurring approximately 5 times during the 2 seconds. This was not evident in the waveform that had a maximum frequency of 3000 Hertz. Expanding the 2-second waveform of the 200 Hertz data allows us to check the time differential between the low-frequency events. We see that the time for one event is 0.4 seconds. This time is equal to a frequency of about 2.5 Hertz. The 3000 Hertz spectrum with 400 lines of resolution has a minimum frequency of 15 Hertz. This event cannot be seen in this spectrum at its fundamental frequency. It has been left out of the spectral and waveform data. The spectral data from the 200 Hertz data has 400 lines of resolution, but includes energy down to 1 Hertz. The 2.5 Hertz is very low in amplitude and will typically be overlooked. However, this low-frequency event is observed in the spectrum. The cause of this frequency is discussed in the next section entitled Modulation. In routine PDM surveys, most measurements are set to include high-frequency data to be sure to capture early stages of bearing wear and other high-frequency energy that can be so destructive to a machine. However, these measurements could be missing low-frequency occurrences that may be the root cause of the bearing failures and other high-frequency energy. Some analysts include at least one low-frequency measurement on each machine component to capture these low-frequency events. For very slow-speed machinery, that is, below 200 RPM shaft speeds, time waveforms may need to be as long as 1 minute to capture transient or very low-frequency events. This data is over a 4-second period. The event occurred once every 2 seconds with a half-second duration. The problem in the machine would have been more difficult to find and diagnose without a long time span in the waveform. Two types of modulation seen in vibration analysis are amplitude modulation and frequency modulation. A third phenomenon, beat frequencies, are often mistakenly thought of as modulation. Modulation is the product of two frequencies, a carrier frequency and another frequency, whereas a beat frequency is two primary frequencies that add to and subtract from each other. Let's examine the waveform and spectral characteristics for each of these phenomena. In the previous section, we used this motor generator set to illustrate the importance of collecting a time waveform that captures low-frequency events. The pattern in the waveform of these low-frequency events is commonly assumed to be modulation. In reality, these may be beat frequencies or true amplitude modulation. An example of a beat frequency is seen in these two independent frequencies that are fairly close together. The frequency of one signal is adjusted to line up with the other signal. As the individual frequencies repeat, they will be in phase and out of phase with each other. As they move in phase with each other, their amplitudes add together, causing an increase in amplitude. As they continue, they will move out of phase with each other until the phases are opposite. And at this point, the amplitude of the two frequencies subtract from each other. This varying amplitude as the frequencies move in and out of phase creates an audible droning sound, which is a beat. Usually a longer time in the waveform is required to capture these beat frequencies. This 2-second time waveform captured 5 cycles of the beat frequency. In the previous section, we measured these and determined that the time for each repeat was 4/10 of a second, which is a frequency of 2.5 Hertz. The area around 120 Hertz is expanded to show two distinct peaks 2.5 Hertz apart. The peak at 117.5 Hertz is exactly 2 times turning speed, and the peak at 120 Hertz is 2 times line frequency. The sidebands result from the beat of two primary frequencies, each having harmonic content. This beat frequency is also present at the difference frequency of 2.5 Hertz. Beat frequencies are common when primary frequencies are less than 4 Hertz apart. Now let's look at frequency modulation. In this example of a gearbox, the carrier frequency is gear mesh frequency. Pure frequency modulation maintains a constant amplitude signal with frequency variations. As commonly seen in industry, gearboxes exhibit both amplitude and frequency modulation. The sideband spacing around the gear mesh frequency is the input shaft speed. Gears have tooth spacing variations which cause the speed of the gear to constantly increase and decrease. This causes the frequency modulation. The gears on this shaft have 48 teeth. The high impacts are spaced at the shaft turning speed. As expected, the expanded waveform shows 48 impacts during each shaft revolution. The waveform data clearly shows the significant 1 times turning speed event. This is a result of amplitude modulation, which is more dominant in this example. The 1 times turning speed peak is present in the spectral data. However, its amplitude is very low and could have been missed by the analyst. As a result of the modulation, this event shows up as sidebands spaced at shaft speed around the gear mesh frequency. Gear mesh frequency is the carrier frequency in gears. Frequency modulation is due to speed variations causing frequency changes. In amplitude modulation, the frequency remains constant and the amplitude varies, causing sidebands around a carrier frequency. These changes in amplitude could be from repetitive load changes in synchronous motors or generators. They could also occur in rolling element bearings as the defect passes in and out of the load zone. Amplitude modulation typically has only one sideband to each side of a carrier frequency, in contrast to frequency modulation, which will have multiple sidebands. However, most applications in industry are a combination of both frequency and amplitude modulation. The number of sidebands is relative to the nonlinearity in the system. The amplitude and frequency modulation differ from beat frequencies in that the beat frequencies are closely spaced primary frequencies, which add and subtract, while modulated frequencies are the product of two frequencies and show up as sidebands around a carrier frequency. The defect frequencies are the carrier frequencies in a rolling element bearing. Waveform data is often the key to diagnosis that might not have been evident from spectral data alone. Whether simple or complex, random or periodic, asymmetrical or truncated, waveform characteristics can truly provide helpful information, which leads to a more confident diagnosis of misalignment, looseness, rolling element bearing defects, gear defects, electrical, and other machinery problems. View the waveform and acceleration to assist you in the analysis. Remember that decreasing the maximum frequency and increasing the sample size increases the time waveform length, allowing very low frequency events to be captured. However, increasing the maximum frequency and decreasing the sample size provide more detail for high frequency events. We are confident that by applying the principles in this program, your vibration analysis skills will be enhanced. Thank you for selecting CSI for your PDM and RBM needs. We look forward to helping you achieve success in your future endeavors.